All right, welcome to Calculus 2. This is the lecture material for Friday, January 29th. Okay, first let me say, I think I told both classes I will be available if you would like to ask me questions about anything, homework or material, whatever, you can text me at this number. This is a text only. Don't try to call it. I don't think it'll go through, but a text only number. I'll also post this somewhere on our XYZ page as well. And maybe every time I make a lecture, I'll just post it at the top. And you send me a text, and again, I'm going to be a couple time zones away and taking care of some family matters. But as soon as I can get back to you, I will, and we can make arrangements, whatever your question is, hopefully get it answered. All right, today I want to talk about the material in section 3 of chapter 2. It's another volume technique. You know, we already have a few ways to compute volume, but you know, it doesn't hurt to have another one. So we'll work it out. Again, just like the cross-sectional method, I'm going to derive a formula for it by finding a Riemann sum estimate. In the end, we're going to have a formula. So I hope you can understand the Riemann sum process. But, you know, and you all will to some degree. But whatever that degree is, it doesn't matter. You know, we're going to come up with a formula, and you know, we need to pay attention to that formula and especially understand when maybe something about our problem doesn't quite fit it, and then we need to tweak it a little bit. We'll talk about a few options, but most of the problems will start with the homework. With the formula. So here we have a function. Like almost every day we start out with some function. It's a positive function. The graph is above the x-axis. And I want to take the region between two values, positive values, a and b. And then notice we're going to rotate that about the y-axis. So, you know, over here there would be, if I draw a cross section, there would be another piece of it. It would look, I don't know, something like that. There would be this hole in the middle. Okay, that's kind of an ugly picture. We'll make it prettier here, hopefully in just a minute, or start with a new one. All right, so, you know, if we were rotating around the x-axis, we'd know exactly what to do. So the new thing here, section 3, is when I have a region that really describes well using functions of x, that is, this function is always on the top, it borders the x-axis, and it goes from a to b. So I really want to use functions of x to describe the region, but it's rotated about the y-axis. So those things are in conflict as far as the first technique is concerned. The way that the variable we like to use to describe the region and the axis of rotation, they were the same for the first technique, and here they're different. And so that'll be one of the ways we'll decide when all is said and done about volume techniques, about which technique should we use. So we'll look at the region and say, well, do we want to use functions of x or functions of y? Or maybe it doesn't matter. Maybe we can do either one. And then we make our decision there. Let's say we like functions of y, just randomly. And then to say, well, it's rotated about the x-axis. Then that means I need to use the new technique. My preferred variable and the axis of rotation are different. One's x, one's y. If they're the same, then we're going to use our cross-sectional, our disc/washer technique. If they're not the same, then we use this new technique, which, by the way, is called shells. All right. So let me create a little space here. Let me pause this while I figure out how to do it. Okay, so let's take our function. Let's go back to a black pen. So from A to B. And we're going to rotate about the y-axis. This function is f. And so what we're going to do is because this is a new problem. It's different than anything we've seen before, so our only hope to find an integral is to go back to the basics. So we'll split the interval into n equal parts. And again, like I always do, I'll use n equal 4 for the picture, but we're thinking n, no, we're not fixated on 4. Okay, and let me take one of those regions and kind of blow it up. Let's pretend like we have this one right here. So we'll go from here to there, and we got the function doing something up here. Okay, and what I want to do is estimate the volume generated by taking this chunk of area and rotating it about the y-axis. Okay, so we're going to rotate it that direction about the y-axis. So because the function's curving in some fashion on the top, geometry can't really do it. But in a Riemann sum, we estimate and hope the error in the estimate will go away. So normally we would call this x point xi minus 1, and this one is xi. Now for this example, I want to be a little bit choosy to find a Riemann sum. Well, first of all, I need to estimate the volume that this slice of area generates when it gets rotated about the y-axis. So I'm going to be picky here. I'm going to take the midpoint, right, smack dab in the middle as my xi star. The previous examples, we haven't been picky about the point, just that we chose one, but we're going to need to be a little pickier here. You'll see as we go forward. And then we're going to run this thing up to the function and flatten it off on top so that geometry will get me the volume. It off. I get error. And we'll have, hopefully, that error will go away as we let n go to infinity as the integral requires. So if this is just a rectangle now, it doesn't look like a rectangle because I can't write very well on these small computer screens. But that's a rectangle. We're going to rotate it about the y-axis, which is going to generate something like this. Okay. So that's like a hollow cylinder. A good name for a hollow cylinder might be a shell. And if you remember, on the top, when we started, we called this the shell method. So that's because our Riemann sums, when I start trying to estimate the volume, they generate these shells. Well, this is a solid we can get the volume of from geometry. So it has a height, let's call it h, and eventually we'll have to write h as a function of x. And then these shells have an inner radius, let's call the inner radius r1, and the outer radius, we'll call it r2. And then v sub I, the volume generated by the ith subinterval, is approximately equal to the formula for volume of a cylinder, pi r2 squared h minus pi r1 squared h. Okay, the volume of the outer cylinder minus the volume of the inner cylinder. And from geometry, we know how to get volumes of cylinders, right? Circular cylinders, technically. So let's factor the pi. And what is h? Well, h, the height of the cylinder, came from the functional value. Right? It's this guy right here. And so notice we can factor that off, and that's going to be f of xi star. And then we'll take it slow here. What's left is r2 squared minus r1 squared. So keep going. Let's write that as pi. Notice I mean, we need to convert the r's to x, and we'll do it slowly as we work our way through this. But also notice we don't have a delta x yet, and if we're going to get a Riemann sum, we have to have a delta x. So maybe converting the r's to functions of x like we need to do, maybe that'll introduce a delta x, hopefully. So the first thing I'm going to do is factor. This is the difference of two squares, so we can factor it. Let's write it like r2 plus r1 times r2 minus r1. Okay? So, take a close look at that while I write these parts coming down. So, the difference of the radii, r2 minus, that's this guy right here. And if we look back at our picture, that is exactly this dimension right here. Let me do it in green. That's the thickness of our shells. That green becomes this right here. And hopefully you can recognize that as the missing, one of the, at least part of the missing detail. That is, r2 minus r1 is just delta x. So, we still have to deal with this r2 plus r1, but let's slip a delta x in over here, and then we'll figure out what to do with r1 and r2. If you notice, again, let's take a look at this picture. So the inner and outer radii are, here's the inner radius, it's the distance from here to there. That is, it's xi minus 1. And the outer radius is the distance from the origin to the end of our subinterval. That is, it's xi. And, when those are the radii, and on this term right here, r2 is xi, r1 is xi minus 1. That's where we got our delta x. But now we have a little bit of a problem. r1 plus r2, if I add, again, xi minus 1 is r1, xi is r2. If I add them together, I'm going to be way over here somewhere. Let's go back to black. This guy, this x coordinate added to that x coordinate, it's going to be way out over here somewhere. It's not on the interval. That's a problem. We need it to be on the interval, otherwise we don't have a Riemann sum. Well, remember, we chose this xi star to be the midpoint. And what is the midpoint? Well, xi star, it's simply the average of the two values. So xi minus 1 plus xi divided by 2. That gets me the point right smack dab in the middle, their average. And notice, let me add in a detail here. We'll take it nice and slow. Like we said before, r2 is xi, and r1 is xi minus 1. So if I convert the r's to x's, I get that. And then notice if I divide by 2, I get xi star. So let's divide by 2. We want it to still be equal. We're saying equal, so if we're going to divide by 2, we have to multiply by 2 as well, and then take a look at what we get. It's fairly amazing. So this equals, let's take the 2 and bring it up with the pi. It's just a constant. This quantity is none other than xi star. Over here, the midpoint. So let's write it in there, and we'll write it before the F, just so it looks better that way. I should go to black. So this thing in red is my xi star, and then I have my F of xi star. And last but not least, and very importantly, We have our delta x. Remember, all of this is equal to an estimate of the volume on the ith subinterval, and therefore the total volume, and by the way, this is a Riemann sum. It has all the ingredients. It's got a delta x. It is a function of a point on the subinterval, xi star, happened to show up twice. That's okay if that's what it takes. And it's easy to believe that as n goes to infinity, that the error in our estimate, so the errors are, we're generating some, we're missing, let me do it in red. We're missing a little bit of volume here by flattening it off, making it a rectangle. We're missing a little bit there. We're gaining a little bit here. Yes, it's an estimate. But it's easy to believe that as n goes to infinity, those little tiny differences, they're just going to go away. The limit will do its magical thing. And so therefore, we can say that the total volume will be approximated by summing over all of our subintervals. There are n of them. And the function that gets us the volume of any particular one is 2 pi xi star f of xi star. Finally, taking the limit as n goes to infinity. I'll write it out and then we'll make an observation. Oh my goodness. So the volume is exactly equal to the limit as n goes to infinity, summation I equals 1 to n, 2 pi xi star f of xi star delta x, which we recognize because this is a Riemann sum. That is the definite integral. What? Let's take the constant out. Actually, that's not yet. It's the integral from a to b, 2 pi. So the function that we integrate is, remember, whatever shows up between the sigma and the delta once we have a Riemann sum. So 2 pi xi star f of x, take the limit, the stars go away. 2 pi x f of x dx. And then finally, let's pop the constant out. And here is our formula. So now, this is how we're going to solve problems. A to b x f of x dx. All right, so let me clean things up. You can see I've got quite a mess, and then we'll do a few problems. All right, we'll start with the really easy problem. Find the volume when the region under the function 1 over x from 1 to 10, x equals 1 to 10, is rotated about the y-axis. All right, so let's take a look at the region. We know 1 over x, a hyperbola, looks something like this. A little smoother. And we're going to go from 1 all the way out to 10. So we're going to take this region and rotate about the y-axis. So we get this nice little cross section over here. You can actually draw kind of a nice picture of this solid. Something like that. It's got this hole in the middle. Okay, we want to find the volume. Well, we look at the region and we really want to use functions of x. Functions of y are really not a good choice. So we prefer x here. We're rotating around the y. Those are opposite, so we're going to use the method of shells. Obviously, the first example is going to be shells, but that's the way we think about it. So we have a formula for it, and this fits it, right? It's exactly like our picture. We have a function on top, interval 1 to 10, we're going about the y, so we can just bring our formula in, and I'll write the formula generically, and then we'll fill in the details. X f of x dx. Notice no squares or anything like the other formula. And of course, a and b are 1 and 10 handed to us. And something amazing happens. The function is 1 over x, which just cancels the x. So we get 2 pi the integral from 1 to 10 of the function 1. Well, that antiderivative is just x from 1 to 10. 10 minus 1 is 9, and so 18 pi is our answer. Units cubed, of course. All right, first example. Let me set up the second one. All right, for this problem, we have the region in the first quadrant under y equals 4 minus x squared is rotated about the y-axis. Find the volume. So the picture will really help us. We know 4 minus x squared is a parabola, 4 units up, opening down. And I made the problem nice and easy. We can tell that this intercept is at 2. So there's the region. And I actually can use functions of x or y. It doesn't really matter. And we're rotating about the y-axis. So I can probably use either method. And in fact, I'm going to. The first method I'm going to use is the new method, the method of shells. And so since we're rotating about the y-axis, we don't have any control over that. And then I need to think of this region as functions of x. And that's the way it's given to us. So that feels natural. And we get a real simple, I'm not going to evaluate the integrals here. I'll let you do it and make sure we get the same value. So by the method of shells, we get 2 pi, use our formula. We're going to integrate from 0 to 2. And then we have x times the function, 4 minus x squared dx. And that ought to do the job. Okay, and just for comparison, side by side, let's do the disk method as well. It is disk, not a washer. And so because it's rotated about the y-axis, for the disk method, I have to integrate with respect to y. So I need to describe this parabola using functions of y. I can do that by solving for x. So if I take my function here and just then solve for x, I get x squared is 4 minus y. And x is one of the square roots. Because we're in the first quadrant, it's the positive square root, 4 minus y. Okay, and then I'll use my formula, if you can remember from the other day. We just get pi, and then we're going to integrate. We're with respect to y, so we're going to go from here, the bottom of it in the y direction, up to the top. That's 0 to 4. The function is the square root of 4 minus y. And the disk method says that's a radius, we got to square it. And if we're going to evaluate it, we love having that square there. Okay, that ought to do the job. Those integrals should be equal. I'll let you work them out. Neither one of them presents any challenge for us. So you can see for this problem, because I can describe the region using functions of x and y really just as easily, then that makes both methods available to us. The previous example where we had y equals 1 over x, that region didn't describe very well using functions of y, and so we didn't do it. We used functions of x. All right, I'm going to show you one more wrinkle on this thing, and then we'll call it good, and then I'll assign homework. Okay, here we have the region between two functions, f and g, with f, one of them, in this case f, always on top. And we're going to rotate around the y-axis, as you can see. So we probably don't need to rederive all the way back to Riemann sums. If we can take a look at the formula we came up with, let me write it actually down here maybe. 2 pi integral a to b x f of x dx. So, and if you think about the role that these things play, the x, didn't talk about this before, but really it plays the role of the radius. And f of x is the height of the shells. Well, we're not changing the radius. I mean, we're rotating around the y-axis. There are no tricks there. By taking the region between two functions, what we're changing is the height. And so I think it follows fairly obviously, and we're going to just write the formula down, to solve this problem, we need to take x, the radius doesn't change, but then our shells have a different height. So we'll take f minus g. Okay, and I think that'll do the job, and I think it's not that difficult to see that that's how we modify this formula to get that. Okay, I'm not going to do an example. I'll let you go to work on the homework. And then we'll see what questions we have, and maybe after doing the homework, we'll have a few more things to say about the shell method. All right, good luck, and let me know if you have any issues. Text me at the number at the front of the video. Talk to you later. Bye. Because I'm flattening